Lesson 118 is titled Completing the Square. This is a way to solve for a trinomial when you can't just factor it into two binomials real simply. For example, if you had this trinomial and we set it equal to 0, that would be a quadratic equation. We also call those quadratic equations in the form ax squared plus bx plus c equals 0. We could solve for the roots or zeros of that by factoring the trinomial into two binomials, x plus 3 and x plus 2, set that equal to 0, and we know that the roots or zeros are -3 and -2. And so that was real easy to do. We have nice whole number factors there to work with. Now look at practice problem A. What if I just change that trinomial that we just had up there by one coefficient in that, or one value in that x coefficient? Instead of a 5x, a 6x. We have a totally different quadratic equation that we cannot just solve by simple factoring into two binomials and getting whole number factors. This is where we use something called completing the square. Before we get started with that, let's just think of the difference of two squares theorem. If we had p squared equals q squared, then we can say that p would equal plus or minus q. If p squared equals q squared, then p is equal to plus or minus q. Keep that in mind as we solve this problem using this completing the square method. And this is a method, it's a way, it's a series of steps to solve a quadratic equation that we cannot just solve by simple factoring into two binomials, getting whole number roots for answers. So listen carefully. Your first step in solving using completing the square will be to move the constant term over to the right side. And so I'll just put a 1 for step 1 here, and we'll have x squared plus 6x. Leave yourself some space between the x and the equal sign, and you'll see why in a minute. And then leave yourself some more space over here and put the minus 6 over to the right. Now, what you're trying to do is you're trying to make a paired binomial, a squared binomial on the left side. And so the way you do that is you take half of the x coefficient, which would be 3, and you square that. And so that would be a 9. Now, you know that the additive property of equality states that you have to add the same value to both sides, and that makes the equation an equivalent equation. It doesn't change it, just changes the way it looks. So we cannot just add a 9 to the left side. We need to add a 9 to the right side as well, a positive 9. Now, on the left, we have a squared binomial. We can turn that into a squared binomial. It would just be x plus half of the x coefficient again, squared. X plus 3 times x plus 3 would equal x squared plus 6x plus 9. You could expand that out if you wanted to, but that does work. X plus 3 times x plus 3, that would equal x squared plus 6x plus 9. And so we simplify that to a squared binomial, and then on the right side we just set that equal to 3. Now what we can do is we can take the square root of both sides. So what we have done is we have completed the square in that second step. We completed the square, we made a squared binomial on the left, and the reason we do that, it allows us to solve for x, because the next step would just be to take the square root of both sides, and we'll have x plus 3 left on the left side equals plus or minus the square root of 3. That's our difference of two squares theorem there. And now we have x plus 3 equals plus or minus the square root of 3. See how we can solve for x now? We just subtract 3 from both sides, and we end up with x equals a -3 plus or minus the square root of 3. Now that's a really strange looking solution there, but we have two solutions, right? Just like on all these quadratic equations, we have two solutions for them. we have a negative 3 plus a square root of 3 and a negative 3 minus a square root of 3. Those are our two answers. Those are the two values of x that if we substitute them back into the original equation, it would make the left side equal to 0. So why do we do it this way? Why do we use this completing the square method? Well, that allows us basically to isolate x. If we create a squared binomial, then we can just take the square root of it and it gets rid of that squared term and we get x isolated by itself. We don't have an x squared term to deal with anymore. We just have one x in the problem, and that is why we use this completing the square method. You could use it on a problem like that original one up there at the top. You could use it on that too. It would work. You would get a negative 3 and a negative 2 for an answer. This will work on any quadratic equation. But you just want to be smart about it. If you see a quadratic equation, you need to think about if you can set that up into two binomials with whole number coefficients, and then you don't have to use completing the square. If you can't figure it out setting it up into two binomials with whole number coefficients, then use this completing the square method. Let's do one more. X squared minus 3x equals 5. Now, that's already in the form that we need to use the completing the square method. Let's just move it around a little bit more. Let's give ourselves some space. You always have to have a little bit of space there between the x coefficient and the equal sign because you're going to put a value in there. And then we'll put the 5 over here. Now, to complete the square on this, and just assume that we have to use completing the square to do this problem. It's a problem that we couldn't factor it into two binomials with integer values for the coefficients. So we have x squared minus 3x. We take half of that 3, and we have to include the sign in front of it. So we take half of negative 3 and just write that over to the side. That would be a negative 3 over 2, and we square that. So we have a fraction that we're dealing with here. That would be a positive 9 over 4. So we add that to both sides. Now we go back and we make a squared binomial out of this. And what we do here, put an x here, then we take half of that negative 3. We include the sign in front of it. So we say x minus 3 halves squared. And that's our squared binomial. You could expand that back out if you want to, and you would see that that equals x squared minus 3x plus 9 over 4. What we're doing is we're trying to get x by itself, and this is how we do it. We create a squared binomial. And the steps to doing it are take half of the x coefficient, including the sign in front of it, square it, add that squared value to both sides, then your squared binomial is equal to x plus the half of the coefficient of x, including its sign. In this case, it was a negative 3, so we say negative 3 halves, and square that. That's your squared binomial. Now, on the right side, we have 5 plus 9 over 4. We need to add those two together, so we need to multiply 5 by 4 over 4, and we would end up with a 20 over 4 plus a 9 over 4. That gives us 29 over 4. Now we take the square root of both sides, and we end up with x minus 3 halves is equal to plus or minus the square root of 29 over the square root of 4. Finally, to solve for x, we move that negative 3 halves over, and we get x equals positive 3 halves plus or minus the square root of 29 over 2. We can just simplify that. Square root of 4 to a 2. Square root of 29 will not simplify into anything else. So a pretty strange looking answer, x equals 3 halves plus or minus the square root of 29 over 2, but that's what we'd expect, right, is two roots for a quadratic equation. One of those roots is 3 halves plus the square root of 29 over 2. The other root is 3 halves minus the square root of 29 over 2. If we substitute those back into that original equation that we have, we would get the left side equal to the right side. Review this lesson as you need to get those steps down. And that's all for lesson 118.